Hey everyone, Mr. Fritz here. We're going to talk about geometric series in this video. So we've seen arithmetic series, we've seen geometric sequences, but now we're going to talk about geometric series. So let's dive right into it. Now, where did I put my pencil? Oh, here it is. All right, it's kind of gross. Let's go for it. So let's talk about what a geometric series is. By definition, a geometric series is the sum of terms in a geometric sequence. So we're using a sequence, and it's a series once we start adding up the terms in that sequence. So for example, if I have some finite geometric sequence like 1, 2, 4, 8, 16, then the corresponding series would be what I would get if I added up all of those terms. So they are very much related, but a series implies that we are summing up these terms in a sequence. If we're adding all the terms in a geometric sequence and it goes on forever, we have an infinite geometric series. So relate that or compare that with these previous examples. These are finite series since we are actually ending with a certain term. So let's talk about how to find the sum of a geometric series. So let's kind of prove the general formula for finding some S sub n. And this would mean the sum of a geometric series for any term m. So if you think about how to just write out a series, it's always going to be the first term, and then it's going to be plus the second term, and the second term you get by taking your first term and multiplying it by your common difference. You're going to add your third term, which you get by taking your first term and multiplying it by the common, not common difference, common ratio, squaring that, and so on and so forth. If this doesn't look too familiar to you, then go back to when we first talked about geometric sequences, so you can recognize that this is how we can generate all of those terms. So I can take this all the way up to whatever my n minus 1 term is for my sequence. What I can do, or for my series rather, what I can do next is I can, so I've identified all these terms as u sub 1, u sub 2, u sub 3, u sub 4, all the way up to u sub n. What I can do then is I could take these terms and actually write what I can do now is if I multiply all of this by r, if I take this whole equation and I multiply it by r, hopefully you can see that I'm multiplying the left side by r, and I'm multiplying the right side by r, and I'm going to kind of distribute that r to all of these terms. So u sub 1 multiplied by r becomes u sub 1 times r, u sub 1 times r becomes u sub 1 r squared, u sub 1 r squared times r becomes u sub 1 r cubed, and so on and so on and so forth, until finally when I multiply this term by another r, this becomes an n to the 1 power. If I multiply this term by r, this becomes just an n power. So hopefully you can see there's a little bit of matching up going on. So if I actually align this so that all of the terms line up with their corresponding term in the original series, there's kind of some nice vertical alignment going on here. So again, what I did is I just took this whole series after I multiplied by r, and I'm just moving everything over a little bit. So now when I do that, if I were actually to subtract this r times s sub n, I get something kind of nice going on, and I get all these middle terms to cancel. All of them cancel, and what's left is this u sub 1 and this subtraction of u sub 1 r to the n. So on the left side, when I subtract, I get s sub n minus r sub n, and that's going to equal u sub 1 minus u sub 1 times r to the n. My goal here is to just solve for s sub n. So I've got two of them, and if I factor out an s sub n, I get s sub n times 1 minus r equals u sub 1 times 1 minus r to the n, factoring out a u sub 1 here. And I can solve by dividing both sides by 1 minus r. So it turns out that if I take this geometric series to some n number of terms and I add them all up, it's as simple as just plugging it all into this formula. So I don't need to keep adding. I can use this equation to calculate the sum for any n number of terms in a finite geometric series. You might also see the equation written like this, and this really is the same thing. If I just multiply top and bottom by -1, I get this same exact equation. It's really the same thing. So it really depends on preference, when you'd want to use which. So these are really the two important formulas that are really identical, and this is to find the sum of some geometric series for some n number of terms. So let's kind of see what this looks like to use this. So let me actually write out that equation. S sub n is going to equal u sub 1 times 1 minus r to the n over 1 minus r. So now I want to find the sum of this geometric series, 2 plus 6 plus 18 plus 54 all the way up to 12 terms. So let's see what's kind of important so far. I know my u sub 1 is 2. I know that my common ratio looks like these are all being multiplied by a factor of 3. So that's going to be 3. And then this 12 here tells me that my n is 12. And that's those are all the pieces that I need for this geometric series equation. So S sub n is going to equal 2 times 1 minus 3 to the 12th power. And that's all over 1 minus 3. So what I can do here is that now this is going to be a rather large number. So I'm not going to calculate this in my head. I'm going to go to the calculator to help me out with this. So I can actually type that all in one equation. So I'm going to use my little fraction button here, and I'm going to write this as 2 times 1 minus 3 to the 12th power. We'll get out of there. And in my denominator, this is 1 minus 3, or I guess I could have just written negative 2, but that's okay. And I'll hit enter, and I get this number right here, 531,440. 531,440. And that is my sum. And actually, if I were really to notate this correctly, I would make this S sub 12, since this is the sum of a 12-term series. Let me fix that 1 as well. So if I were to take all these numbers and take that pattern out to 12 terms and add them all up, this is what I get. Notice this is not the same. This is not equal to u sub 12. U sub 12 is the 12th term, where S sub 12 is the sum of first 12 terms. So there is a difference. These are not the same thing, so don't get it twisted. U sub 12 is much different. Finding the 12th term is much different than finding the sum of the series after 12 terms. So I just want to make sure I highlight that. Let's see another example where we are going to find just the formula. So this is an infinite sequence, or an infinite series rather, and all I want to do is just find what the general formula is, S sub n. So again, we're going to follow the format S sub n equals u sub 1 times 1 minus r to the n over 1 minus r to the n. So just like last time, we want to identify the important features. So this is my first term. So u sub 1 equals 9. And it looks like in this case, I'm multiplying by a negative 1/3 as I move from term to term. And if you ever weren't sure, if you couldn't see that right away, we can just take two consecutive terms, and divide them. So we'll take the first or the second term and divide that by the first term. Because remember that if I take u sub n plus 1 and divide it by u sub n, this is how I get my common ratio. So I could have easily taken negative 1/3 and divided it by positive 1 to give me that ratio of negative 1/3. So more than one way that you can do this. So my r is going to equal negative 1/3. And really that's all I need to do for this. Now I can put all the pieces together and I can come up with my general equation here. So the series of this geometric series up to n terms is going to equal 9 times 1 minus negative 1/3 to the n power, all over 1 minus negative 1/3. And at this point, I'd probably simplify this a little bit, clean it up. So let's make this 9 times 1 minus negative 1/3 to the n. I can't really do much there. But in the denominator, this is 1 plus 1/3, so that's going to be 4/3. And then I can actually take this a little bit out even further. I can multiply by the reciprocal to get this thing into the numerator. I can think of multiplying this by a 3/4 over 3/4. And so then this is going to all become my final equation of S sub n is going to equal, this is 27 times 1 minus negative 1/3 to the n power. And that's all over 4. So there we have it. So here's a couple of examples that I'd like you to try. Here's the first example, very much similar to the first example. So pause the video, try this, put in the work, because if you try this, you are actually going to get it much better than having just watched me do this. So I know how to do these. I want to see if you know how to do them after watching that example. So pause the video and then resume when you're ready to see the answer. All right, and here is my work for this problem here. So check through it, make sure it looks okay, and hopefully you got it. Here's another you try. This one's a little bit trickier than I think the last one, but again, we're trying to find the general term or the general equation for the series up to n terms. So pause the video, give this one a shot next. All right, and here is my final solution hanging out over here for this problem. So hopefully it went okay. If you just left this as 1/10, that's fine as well. I chose to write it in this form.